let's start. So, yeah, we're entering the last chapter of the book on distribution theory, and it's another one that's usually not taught in a first course. And actually, I hadn't studied it like formally before, so I found it quite interesting. And so, but the general idea is that in distribution theory, you want to generalize function in some way, and so that you can make sense, for example, of solutions of PDEs where if your initial, whoops, I need to set my status to do not disturb because I just got pinged. Sorry. So it's not uncommon, say, when you're doing PDEs, that your initial condition is not in the domain of your operator, and so it does not really make sense to speak of a solution, but in the usual sense. But you can still like define these objects or these distributions that allow you to find some like to say, okay, what the distribution should look like. So yeah, the sort of one sentence definition of a distribution is that it's a continuous linear functional on the vector space of test functions on RD. But we'll unpack that a bit. But these are quite common, for example, in control theory when computing the impulse responses. So, for example, basically the sort of the canonical distribution is the Dirac distribution, which is in fact not a function but actually a different object. A nice thing is that you can generalize the derivatives for distributions. And you can also talk about the generalized Fourier transform, but there is a price to pay for that, which is that we have weaker axioms, and in particular we have a topological vector space of these test functions, but it's not a metric space. So we have a topology but not a metric, so we do lose something in the process. So the definition of a test function is simply a function from, say, Rd to the complex number that is infinitely differentiable, also known as smooth, and has compact support. So basically you can take the derivative and it's continuous anytime you derive it, differentiate it, and it's only non-zero on a compact set. So basically you can always find some interval where outside of that interval the function is bounded, or yeah. And these form a vector space in the sense that you can add them and so forth. And okay, it might seem a bit strong that to say, okay, we want them to be infinitely differentiable, but it's fairly easy to find some examples. For example, this phi x here being defined piecewise as interval -1 to 1 as e to the minus 1 over 1 minus x squared and 0. And okay, I don't have a nice picture of that, but it looks like a bit of a bump, or like this function. It looks kind of like this on the so the idea is that, okay, you're really looking at like small pieces of the real numbers and getting functions on that. Yeah, they're vector space because you can like translate them and scale them, and you can add them no problem. A nice thing is that because we've taken them to be infinitely differentiable, we can always apply any differential operator to them, and it's still in the test function. So that's nice. And we have a special notion of convergence of test functions, which is that if we have a sequence of test functions that satisfies these two properties, one, there's a compact set such that all the phi n vanish outside of k, so basically the support of each of these distributions does not explode, and that the phi n converge uniformly. So uniformly here means that the absolute norm between these functions has to be to converge to 0. And under this notion of convergence, note that it's not. It might look like a metric space because you asked for the absolute uniform convergence, but we also had this condition on the convergence for the support, and that means that it's a topological vector space because we have a notion of convergence and there is a topology that generates it, but it's not a metric space because there's no metric that generates it because of this first condition. So we can actually now move on to defining what a distribution is. So a distribution T on RD is just a map, a linear map from the space of test functions to the complex numbers, and so it's linear and continuous. So essentially, we're taking the dual space of the test functions, and it's fairly trivial to show that it's a vector space, and we have that if phi n, because it's continuous, it's reserved on the limits, and we have this sort of slight abuse of notation where we denote that the linear form applied to phi, a test function, is simply we denote as just a inner product. And the book mentions that to check that a given distribution is continuous, it's enough to just check with some sequence of phi n that converges to 0, and they give a proof why you can always reduce it to that. Okay, so then we have an example of these test functions, notably locally integrable functions. So a function is locally integrable if for any compact set the integral of the absolute value of this function on this compact set has to be finite. And pretty much most functions you can think of, unless they diverge in finite time, they will be locally integrable. And so this induces a distribution TF, also known as a regular distribution because it comes from a function, where we define simply the integral of our function with the test function. And because it's well defined because if any test function has a compact support, so this integral is always finite. So it's easy to show that's linear, and the continuity is again fairly easy because we can always reduce it to our compact set, and we know that if we assume that phi n goes to 0, then this norm here goes to 0, and this integral is bounded, so it has to be 0. So we have one fairly general example of distribution, and sort of the canonical example of a regular distribution is known as the Heaviside function, which for ML people it's the derivative of value. So it's just a function that for negative numbers is 0, for positive numbers is 1, and at 0 it's not clear what it should be. Like it can be essentially whatever we want. So this is an example of a regular distribution, and in fact it's in control is the classical example of, I mentioned the impulse response. This would be the step response where you have a system that has an input, and you're basically looking at what the system does when you set the input to 1 and don't move it. So we have a theorem on equality of regular distributions that says that if we have two regular distributions TF and TG that are equal as distributions, then the functions f and g are equal almost everywhere. So beware that the book does not go into the almost everywhere and Lebesgue integral, but basically, except on a set of measure 0, these functions have always the same value. So a corollary of that is that we know that the set of locally integral functions on RD is a subspace of the set of distributions, because the functions themselves are a subspace, and they give this hierarchy of inclusions where at all the way at the left we have the test functions, because trivially they also induce distributions. They're a subspace of the smooth functions, which are themselves a subspace of the just n differentiable functions, which are part of the continuous functions, and beyond that we have the locally integrable and then the distributions. One interesting thing is that okay, all of these spaces they have actually the same cardinality as the real numbers, which might be surprising, but it's it's not too hard to actually show that. But so these have essentially the same cardinality as the real numbers, but beyond that, I'm not sure. So in particular, I'm not sure if the locally integrable functions are have the same cardinality as continuous functions or not, and for distributions, I don't even know either. So maybe we can discuss that. So, but not every distribution is regular, in particular the Dirac delta, which it's often mistakenly called the delta function, but it is the distribution. And it's basically defined as the distribution that evaluates your function at 0 or at some point a. So it's your evaluation functional. Note that there are also actually some issues with the delta in some spaces, especially Hilbert spaces. But yeah, it's not a regular distribution, because if we were to plot it as a graph, you'd have a function that is 0 everywhere on the real line, but except at 0 it should be infinite. And so this is not a proper function, but it's a distribution and it works.
Regarding the L1 thing that you mentioned before,
the locally integrable.
yeah, whether it has the same cardinality as R. I was thinking, for example, if you consider the interval 0, 1, so we define them on the compact interval 0, 1.
Mm-hmm.
I could define an L1 function which is essentially like 0 on some real numbers and 1 on other real numbers. So that's an L1 function. I can define it like pointwise, essentially.
Yeah.
So I guess that wouldn't be that would prove that the cardinality has to be higher.
So
because
remember, it's 0 on which set?
on like essentially you want to, if you want to prove the cardinality is higher, you want to prove essentially that you can construct a sort of power set.
Mm-hmm.
So you can maybe define it essentially as a function that is 0, 1 on some specific numbers.
I feel like you have to be careful about whether the set you choose is measurable.
Yeah, that's one tricky thing. Like, for example, we can define your function to be 0 on the rationals and 1 on everywhere else, but that's essentially the function 1. So like it's so
Yeah, so
like the question.
the almost everywhere equivalence can make sense.
Yeah, I think it's more of a question about just integrable function, where okay, is like L2, like when you take the quotient by almost like with almost equal, is it still larger than the Aleph2 cardinality or beyond? So I'm a bit curious. But I think like the general idea of distribution is that you're assuming that you're working with just smooth functions anyway most of the time, so it's not even really a concern. But
But maybe then under some view, like if you consider the space of sequences, which is a bit easier to think about,
mm-hmm.
it's a bit like R, Cartesian product of R, accountable amount of times, and that shouldn't, that is still uncountable as a set. So if I view a function like maybe as a uncountable product of R, maybe you can say something about that, whether it's
Yeah, but then the problem is that you have some topology on it. So, but I mean, I don't have the answer either. So, but there's some unclear, like, yeah, details about the cardinality of these objects. But anyway, so yeah, we have some another example of a distribution that's with a function that is not locally integrable. So we take the 1 over x. But that we define an operator such as this way, as the limit as epsilon goes to 0 as of the integral of over the points with norm larger than epsilon of phi of x over x. And this is called the principal value of the principal value of this integral, and it's actually well defined. And the way to show that is that okay, you take some phi of x being just phi of 0, such that phi of x is equal to phi of 0 is equal to integral of this, and you get just phi of 0 plus the integral of x times the 0, 1, so the integral of the phi prime tx. We assume here that the phi has support at least contained in the interval minus AA. So we know that since for between a and epsilon this integral is 0, actually, yeah, because it's a symmetric function, we know that this integral eventually goes down to, like, we can do some work and find that okay, we have something that does not blow up because we have the integral of the like basically our interval over dx times the integral of phi prime, and this actually has to converge to a limit as epsilon goes to 0, and so the function is well defined. So this is an example of another distribution, but that is not regular. And yeah, as I said, we can actually define some pretty weird distributions. But then one really nice thing about these distributions is, okay, we don't have necessarily a nice topology, or at least it's not a metric topology, but we can still define derivatives for these distributions, and the way is basically using defining the derivative operator as the self-adjoint, the adjoint of the derivative on the test functions, because we know that these test functions are always differentiable, and so the derivative operator is well defined. And because it's a linear operator, we can define its adjoint acting on the distributions. And so it's simply defining the derivative of t applied to phi as simply minus t times the minus the operator t applied to phi prime. And yeah, the minus sign here is because, at least if you think of the Hilbert space, the derivative of operator is Q adjoint, because its adjoint is minus itself in some way. And by just defining it, okay, we get some interesting properties that, okay, if we have a regular function, then the derivative simply, like the derivative of tf is simply t of f prime. And
so regarding the distribution of derivative, it also comes like originally from how physicians did it, like via integration by parts.
yeah,
So I guess that I didn't know about the inverse sum you were mentioning. Regarding the
yeah.
minus sign, I didn't know what you were talking about.
Yeah, I mean, it's really, I guess, yeah, of course it came from the physics in the beginning, but mathematically, if you look at just the differential operator on the Hilbert space, and you ask, okay, what should its adjoint be, and you're computing this integral of the derivative, and you can do the integration by parts, and that gives you a minus sign of the derivative. So that's how basically you get that the adjoint of the derivative is minus the derivative. But here it's sort of defining it in that way so that it works, and as a result we get a bunch of nice properties. Okay, so we have a fairly easy proof for this case. But okay, that's for regular distributions. We can also ask, okay, what does it look like for, say, the Heaviside function? And okay, by doing some work, we find that actually the distributional derivative of the Heaviside function is the Dirac delta. And this kind of makes sense because if you look at the Heaviside function, it starts with 0, then it like has a jump, and okay, you can think, maybe that jump is just like you can imagine just giving a flick to the function that it has to move in a discontinuous way. And this is actually formalized in the terms of what's called a jump rule. So I noted that we can actually take the derivative of the delta function again to get basically the evaluator of the derivative. So yeah, the jump rule is sort of the generalization of or formalization of this, is that if we have some f, a function that is continuously differentiable on R, except at maybe some point A, where the limits, the limits at these points are well defined for both, like coming from both sides, both for f and its derivative, and basically it means something like this drawing here, where we have a smooth function almost everywhere except this point where it has a jump. Then okay, we have that f and f prime are locally integrable, and the derivative is okay the standard like t of f prime plus a term that describes a jump from one value to the other. So we have the limit f at a coming from the positive numbers minus the limits at a coming from the negative numbers, and we have all that times a Dirac delta. One side note is that this sort of, like I think the word distribution also sort of can make one thing of probability distribution, and I think in fact it's related because you can have probability distribution with these jumps as well. So yeah, the proof again is fairly mechanical. You just have to like just unroll the definition and eventually you get there. So it's not particularly difficult. One nice thing is that we can generalize the jump rule for easily for finitely many discontinuities, and actually even for countably many discontinuities, but under the condition that it has to be locally finite, meaning that for any compact interval there's only finitely many discontinuities in that interval. So you cannot have like a sequence of discontinuities that get closer and closer. In that case, it doesn't work. And the book gives an example of the function that you're deriving is just the integral part. So it looks like just a stair, right? So just this is the identity is just the stair. And then if they derive that, well, basically you're just having a jump at integers, and the derivative is basically a train of Dirac deltas, an infinite train of Dirac deltas, and this function or distribution actually has a name. It's known as the Shah function because the character here is the Cyrillic, the Russian character Shah, and the funny story is that people chose it because it looks a bit like a coomb or like the function, so it's like a funny symbol for a function because of what it looks like intuitively. Okay, so I have my NAR slide. So we were just doing the first two sections for this case, and yeah, of course you can, for distributions on d-dimensional space, you can define the partial derivatives as well in exactly the same way. So it's not a big trouble. But then if you want to look at okay, what should the Heaviside function or other cases look like, it's a bit more work. And one thing is that the last part of that section is about Sobolev spaces. So Sobolev spaces are basically what happens if you take some space of functions that are integrable and their derivatives are also integral, say here in L2, and we have a special norm on them being just the sum of all their norms, or the norm of S plus the norm of all the derivatives. And this is a Hilbert space of functions that are here differentiable. And these Sobolev spaces are very they're usually what you work with when doing PDEs at some level, because they're basically the space of functions that are really well defined, although note that here we're talking about distributional derivatives. So it's one way to get a Helmholtz space of functions that you can differentiate, and so it's sort of a natural space to work with when you're doing PDEs. Okay, that was all my sort of.
What do Sobolev spaces of function of distributions? I mean, what do you do that Sobolev spaces of functions don't?
Like the whole point of doing these distributions is that you can get, like, say you have say you have like the heat equation. So du d is the not a u. Say that here is just the second derivative. Implicitly, that means that u has to be 2 times differentiable. But say now that you're solving for the heat equation, but your initial condition is actually not in the domain of this operator. Say that your initial condition looks like something like this. So this is a function that is not differentiable, and so it's because it's not differentiable, it's also not 2 times differentiable. But you still want to talk about the solution of the heat equation for this initial condition. And in that case, okay, you cannot use the. It's not quite the same as the strong solution where you assume that your initial condition was in the domain of that operator. But if you jump to the distributions, then okay, this is not like this function is not differentiable in a classical sense, but in the distributional sense it is. So because of that, that means that you can find a solution or a weak solution. So, but that's part of the next section that we haven't read yet. That you can express these solutions in some way.
So in this example, is the Sobolev space just the natural space where the solutions of this equation live?
Yeah, pretty much.
Unfortunately, in this example in particular, the actual solution becomes smooth immediately because of the regularity of this equation. But if you had some other type of equation, like the wave equation.
Yeah, like the wave equation,
then that with a non-differentiable input, essentially, like the non-differentiable zero time function, you get a non-differentiable solution also. Like you keep the discontinuity.
yeah, like if I remember correctly, like say that you're solving the for wave equation. Note that here we have a square. If I remember correctly, because it's been a while, but the wave equation, what happens to say this initial condition is that it gets split into 2 trains. You get like a smaller train of.
A forward traveling wave and a backward traveling.
Yeah, you get a 4. Yeah, but then the waves are just the. Yeah, but then what happens is that it's just a small. It's still non-differentiable.
Yeah, also like in optimal control, they are quite important because like if you want like a Dirac delta as an impulse, like you can handle like not just controls but also physics. For example, like when we talk about I push an object, but I don't want to accelerate it, I can talk about using impulses. So that also
Yeah. One thing that I think that's probably going to be covered in the next section is that when doing PD, you have this notion of the green function or the fundamental solution. So, gosh. And so the green function is just the solution of your equation with the Dirac delta as input. And the reason it's important is because when if you have this green function, you can basically use it to recover the solution, to compute the solution for any other initial condition. I think it will be covered, but like the rough idea is that you get, because the you can think of the green function as, yeah, okay, it's the way a single delta propagates, and so if you sort of imagine like an arbitrary function as just like an integral of deltas.
Well, like use the example with the heat equation. I think it's the simplest one. You have a convolution with a Gaussian.
Yeah, yeah, exactly. So for the heat equation, the delta just becomes a Gaussian. Okay, it's a fat Gaussian, but at least for some time it eventually becomes a very wide Gaussian.
Yeah, the green function can also depend on time.
Yeah, it usually does. And so if you want to find, like, have some arbitrary initial condition, you just take the convolution with the green function for the time you're trying to solve, and you basically have your solution for arbitrary functions. But then to do that, you actually have to step to the distributional sense to even like to have it, for those things to even make sense.
Yeah, in general it won't be smooth. So in the heat case it's super simple, but
Okay. Any other discussion that we want to make? Maybe some of the exercises. There were like quite a lot more exercises for this part than last one.
I just jumped in, so
Yeah,
distributions today.
yeah. So you haven't seen the exercise, but there's like 15 already in this section, and they started pretty nice. But the last few ones are like much more difficult, and I didn't quite enjoy all of them. Like the last one I found was a bit bullshit.
For example, like I have the book open of exercises.
If you look at like 6.15, it looks scary, and actually it is. Like it comes out a bit of nowhere. Like the first exercise are really nice. It's like, it's fun. It's very short to solve, and then you have this awful thing that lands on your lap.
Let's see.
I haven't done exercises for this section yet, so if we're going through them, I might want to duck out so as not to be spoiled.
Okay. Yeah, like most of the exercises are pretty nice. Like they're easy to solve and they're pleasant, but the last few ones I found were like really not fun. Like for the 6.15, I actually looked at the solution, and like even now I'm still not sure I understood their solution. So it seems a bit overkill.
The Laplacian one seems. I recall it a bit from physics, like electromagnetism, that logarithm in there.
Yeah. I mean, I think this actually is an example of
Ah,
a green function, even though they don't call
and
it.
also, like this is already a bit applicable for actual machine learning purposes because like there's the whole like literature on neural operators and whatnot, where essentially by phrasing things as a convolution, for example, you can solve problems because then you have like a prior, you already know that your solution has to be of some form, and use deep learning to learn it. So like this is already quite useful.
Yeah, but in practice, don't they just like have a layer where they convert it to for a Fourier basis, like have just a linear layer on the Fourier and then convert back, maybe truncating.
Yeah, in the Fourier neural operator, yes, but essentially, like the idea is still like the Fourier stuff. I think is still to do some convolution in some sense. Like if you multiply things after a biasing it to develop a convolution in some sense. So, but I mean, like the general view can be helpful. Like if you know that, okay, like for example, instead of solving a specific differential equation using deep learning, you can learn how to find the actual pin function. So you start with a lot of initial conditions, you learn the green function, and once that's learned, you can use inference on that and generalize extremely well for new input distributions.
Yeah, that's interesting. I think Zoe was working on something like that at some point, for Julia at least, but I'm not sure if she got it done because she it was not a fun project apparently.
I've seen also some things like in optimal control, where the differential equations would be very, very high dimensional. So there was some work also on doing that, like finding a value function for an optimal control problem. It isn't necessarily too linked with this, but I think like getting a little bit into differential equations can help solve actual real world problems, even if you use deep learning. Like right now, a lot of people are trying to bridge the gap.
Yeah, I mean, I'm actually more interested in like the other side of people like putting neural networks in already existing ODEs to like find the missing term, and that usually works pretty well. And you can even use some interpretability tools to find what the missing term should look like.
Personally, I like some work. Ideally, I wanted to see in a future where neural methods dominate on finding solutions numerically. Like you can just use a neural solver and it spits out the solution faster than traditional stuff, at least on harder things. There's some work on it for climate-related things like prediction of weather. Even Google is working on it.
I think there's like basically a bunch of people doing that in Julia, where they have like this neural surrogate of climate models, and they but yeah, definitely they're just like approximating these stiff and evil equations that take ages to solve. That's an interesting application. Okay, do we maybe like still want to do at least one of the exercises in session? Maybe one of the earlier ones.
Which one did you have in mind?
Let me look. I'm trying to find just even the first one. Wait. The 6.1 is maybe not the fun one, so let's skip that one. It's not great. Let's see. I think 6.3 is actually pretty important, so it's a useful. So I'll write it down. So 6.3 is to show that the set of test function, so the set of derivatives of test functions, so phi prime for phi in the R. The goal is to show that this set is equal to the set of phi in D, such that the integral of phi over the real numbers is 0. And so that's the first pass, and then it's also show that so this is called, they call this set y, that for any such function in y, then we can find that then the sort of integral or the primitive distribution, not distribution, test function, such that its derivative is equal to phi. This has to be unique. So yeah, I remember this one is not super hard to do, and it's actually relevant for the next, like pretty much the rest of the sections.
So I think inclusion one way comes from the compact support condition. So yeah, if I have some phi in P of R, the limit as x goes to minus infinity of phi is going to be 0. But if x goes to positive infinity of phi is going to be 0. So
Note that so it's not true. So maybe to
It was the integral of phi prime.
I'm not disambiguating between capital phi.
maybe starting from the inclusion in this sense, it's like if you take just a test function phi, note that it's not always the case that the integral of phi has to be 0. You could have like a bump, and so this bump would have just a positive integral. But the point is that if you take the derivative, then it's always 0. I think like here it's pretty straightforward to just start computing the integral of phi prime, and let's say that
Yes.
let's say also that the support phi is like some interval AB. Maybe it can be 0 in AB, but like definitely outside of AB it's 0.
Sure, so then that integral reduces to the integral over AB, and that's phi of B minus phi of A, which is,
Yep.
which is this answer.
Yeah, that's the easy part, and I think the
And then to go the other way, you can take the integral from minus infinity to A of your phi prime. And that's a unique way to recover the value of capital phi.
yeah, pretty much. So yeah, so if you take like some phi with basically the same as above, and you take like if you do just define phi, big phi as so the integral from a to x of phi of x dx for x greater than a and 0. Otherwise, that basically works in the sense that you can trivially just derive big phi and it works. And then the only thing left is uniqueness. Like maybe as a small hint that okay, why is the primitive of a function not unique in general, but is it still the case here?
Okay, up to a constant it may not be unique, but here we start always from A. So
It's more that like you could have like like it's usually you'd have phi plus a constant, but here because it's supposed to be have compact support, C has to be 0.
Um,
So
Okay. Right, and in any case, we have this definite integral
yeah,
with freedom.
yeah, but the constant thing I didn't
I mean yeah, it's just usual derivative and integral nonsense. But yeah, this part, like this exercise actually comes up in the later exercises quite often, so it's good to have done it. Let's see. Should we have a crack at another one? I'm trying to look for a fun one. I think maybe one that I can try and jump in the later ones, which I found interesting and not too painful to do, was about showing that if you look at like the Dirac deltas and the derivatives, those are linearly independent. Let me find that one.
That is 612 on page 242.
Yeah. I mean, there's like first, there's like 6.1, 6.11, and 6.12. I mean, I don't think it relies on on like the exercises that were just before, because those are a bit more difficult. But yeah, show that for all and the derivative of the Dirac delta, so the nth derivative of the Dirac delta is different from 0. Here, different from 0 being like in the sense that we can find some test function that does not get mapped to 0 under this.
So we can basically pick a test function that has non-zero derivatives all the way down at some point.
Yeah, but then you'd have to construct one, which might be like it's not so easy to actually construct one. But if at least you can find.
It's not so hard. You can start with something that looks like e to the x somewhere in the middle, and have it brutally run down to 0 instance. I think our e to the 1 over 1 minus x, whatever it was, if you take that and translate it, that should satisfy the condition.
Yeah, and
Although it's even. Well, okay, but it's not
Well,
even when you.
yeah, there's a few complications, but one nice, like I tried doing something smart as well, but like eventually I found a neat trick, but I'll try and like give some
I
hint.
was thinking also that you can use the
But is the
I mean the
Sorry, go
definition of
ahead,
the
go ahead.
distributional derivative and apply it 10 times. So it keeps alternating sign, and then the derivative passes to the test function.
Right, so once you get a function of the correct class, you can just apply the self-adjoint principle
Yeah, I mean,
of the distribution.
like if you apply it once, you should get minus delta and phi prime. So it's minus like if the Dirac delta is the evaluation of the function, Dirac delta minus Dirac delta on phi prime is the evaluation on the derivative. So I think this explicitly tells you, like, if you repeat the argument, that aside from the sign that keeps changing, you get that the derivative will be the evaluation of the nth derivative of the test function.
Yeah, that works. Although there's like I am trying to gesture at like the neat way you can actually construct these phi, and because like you can find some phi, so like it's enough to find that for any n you can find some test function phi n that is non-zero under this, meaning so being called phi n, let's say at 0. But like you can actually construct these phi n in such a way that the derivative, the nth derivative is non-zero, but all the other ones are, and it's actually useful for the next part.
You mean a polynomial?
I mean, you can try polynomial. I did that too, and eventually, like you can try and construct polynomials to like interpolate. It works, but like there's an even simpler way to get one.
I don't know. I'm not coming up with it.
Let's say okay. Let's say you start with like some phi. That's a test function that is non-zero at 0.
Maybe integration multiple times.
You mean integrating the phi?
Yes.
But then is that still a test function?
It might not be.
Okay,
And I think if you do it enough times,
let me give you a hint. Like take the function x times phi.
So you say the derivative of this will be x prime
Which-
phi prime x. Right.
Sorry, it should be. Wait, I think I'm. Yeah, no, that's correct. Then evaluate this at 0.
Phi of 0.
But then this at 0 is also 0, right?
Mm-hmm.
And so, like the general case, if you take xn phi and you say take the mth derivative, you like the general sum you can apply it in basically looks like Newton's formula. You have so from k starting to 0 to m, k to m of the kth derivative of xm times the phi sorry m minus k. I'm sorry because I'm realizing I'm showing the solution, but then that might be a sort of a spoil. So sorry about that. But yeah, the general is that if you just take xn x to the n times phi, when you derive it m times for m smaller than n, this has to be 0 because you always have an x with a non-zero power. But then if you take the nth derivative of it, You go to n, and then that means you have a term of like
You mean evaluated at 0?
yeah, evaluate if you if you evaluate it at 0. So
Yeah, like above. If x remains to some positive power, then it turns everything to 0 because there's a product.
yeah,
And when it becomes a constant, then you look at phi, and if you derivate one another time, the constant vanishes, so it becomes 0.
Yeah, so this makes a lot of sense when you think about I as its Taylor series. When you multiply by the constant F function, you're just pushing everything, those
yeah,
many terms down.
pretty much.
Yeah, okay.
But yeah, so, but sort of the nice way thing, the nice thing about this is that okay, we have some functions that are such that their nth derivative is non-zero. So we have shown that the delta is non-zero. But it's also true that for all the m before n, the derivative is 0. And you can use that for the next exercise to show, okay, because we can construct a sequence, we know that that delta 1, delta prime, and so the derivatives are always linearly independent, because you can always find, like, just by using this function, you're showing that you could not express the you could not express the nth derivative with the previous ones. And so that sort of gives you the linear independence of these deltas. But if you want maybe another intuition as to these, like you're multiplying by xn, it's kinda what we're doing with, like, I think Hermite functions, or indeed splines, where I started doing this using trying to use Hermite splines, where you have a polynomial that's on that's such that okay, you like pick some points. You want I want my polynomial to have these values at these points, but also you want fixed values of the derivatives. And so I tried to use that, but it ended up being overcomplicated and still wasn't sure if it actually was smooth. So after that, I just sort of recycled it for this, and it worked.
Yeah, so to repeat, like you meant to prove the linear independence of the deltas of different orders, and you say that by constructing this example where they can be at 0 on everything, like to any order you want, essentially, that allows you to say they are independent, like some.
Yeah.
Like you're building essentially a triangular in some sense.
Yeah, more or less. Like, sort of like say you have like some arbitrary linear combination of these deltas. Up to some n. Like if you
Okay, if you apply them on the xn to the power of p,
if you apply to just some phi of m in your sequence, that just gives you the mth coefficient, because it has to be like it's 0. Actually, it might not be. Huh.
that was I meant with triangular, because like the lower order things may have some more terms.
Yeah, actually, you're right.
At the very least, I can take the delta of the highest order in that finite
Yeah.
set and use the test function of the corresponding order.
Yeah. Yeah. Okay.
That's
It
definitely
may be
not
okay.
zero.
This
It's
this really is not true, but
operator is not zero.
yeah.
Yeah, so in general, like you might have higher order terms in with the result there, right?
Yeah. So there should be some other terms maybe.
Yeah, but the index may all be or either degrees or things like not like alpha n minus one, alpha n minus two, or plus one plus two.
But this doesn't matter because it's a finite sum, you can always find.
Yeah. It's like essentially like a triangular matrix, like to show that is
Yeah, but then because you can do that for any n, you can say that just the sequence of the deltas are linearly independent. Although I don't think they're a basis in any respect, but it's still fun. Okay, I think we can call it a day.
I will also go to now.
Okay, that leaves basically the last two sections, which are only 10 pages actually, so slightly shorter than this time.